Oh, an update later. Okay. So we're done with the Head for C book, and I think it's yet another good yet another good stopping point to just buff up our C skills. So I kind of want to take the next few videos and just do more data structure stuff to improve our programming skills and just get ourselves ready for more complicated things. I'll admit, I don't even have anything like truly planned uh, going forward. Um, so I think I think doing data structures is like a nice, easy way to just keep up um, with whatever we've learned. So yeah, today's going to be trying to implement a binary search tree, so like a BST. Okay, so binary. You know what? Let me just maximize this. There we go. A binary search tree, and I'm assuming a lot of people actually are kind of experienced in some sort of data structure stuff, but it's basically a special tree where we have something called a binary tree normally, where it's just think of it as like you have one specific node, so that's like a node, kind of like our linked list node, except that instead of having one pointer to the next, we'll have two pointers that indicate left and right. Okay, so this is a binary tree. All of this is a binary tree. Binary in that there's two children. So two children. Okay. What makes it a binary search tree? So is the property. That main property is left child of the root. Okay. Left child should always be less than the root. And that's the root. This one is the root. And this is a node. So left node, right node, root node. Okay, so these are all called nodes. Nodes. So left child's value should always be less than the root value. Okay, value. And the right child's value should let's just say it's always greater than equal to the root value. Okay, so then something like this is actually a valid binary tree. 5 as the root, 1, 6. Okay, we need to take it a step further, and actually 1 can also be itself another binary tree. So this could be 0, maybe this could be 3, maybe this could be, I don't know, 5. Again, you could have repeat nodes, and this could be 8. So I'm sure people have seen this type of structure before. So it's just basically a node that chains both a left and a right rather than a linked list. So this is the most important property here. Oops. What makes a binary tree? A binary search tree is this. Very important. Okay. Left child's value is always less than the root value. Right child's value is always greater than or equal to the root value. All right. Next thing. So going back to the linked list, node, there was actually no specific ordering enforced for linked lists. So then they look like this if you were to draw it. So we'll have some value that points to null by default. Okay, and let's just say value is again 5, right? And then next will be null. Next. Okay, contrast that with binary search tree node. Now, it looks more like this. Okay, left, right. Okay, and then we can say V is 5. If you kind of like think about it and turn this around, it looks kind of like this. And we say this is null here, this is null here, and we can say this is null here, this is null here. Okay? Alright, so we've named these pointers left and right. But it's pretty much, if you think about it, like this node here is just like a linked list with 2 pointers. It's just the same thing as this, really. Next 1, next 2. That's all there is to it. It's just basically the advantage it has is not only does a binary search tree node have 2 nodes, or yeah, points to 2 nodes, but there's a specific order to it. Okay, so left, right, think of it as next 1, next 2, but we'll normally use it as left and right. We'll refer to a binary search tree node to be a node that has a left and right, not next 1, next 2. Okay, so in code, when we had a linked list node, we did something like this. Type def struct, then we can just say node, just for the sake of it. Then we'll say a node would have something like an int value. It's like a linked list that stores integers. And we also had a recursive pointer to struct node next. There we called that a node. Okay. So that's how we initially declared the linked list node in code. So this represents a linked list node. Well, what we can do to represent a binary search tree node is just extend our linked list node, conceptually. Instead of having 1 pointer here to another node, for example, we just have 2 pointers. So type def struct node. And we can say int value. We say struct node pointer left. Okay. Then we have a pointer to the right. with node. Not too different, not too different. Just the only thing different is the pointer here. It's called next. This is called left and right. Just distinction. You go if let's say you live in a world where you can always remember left to be next one, right to be next two. You could get away with that, but that's bad practice. You're supposed to be able to create readable code. Okay. Now, so we have this sort of code visualization now that represents a node. So going back, just bear with me. We're going to go slow. This linked list node looks like that, basically. And B would be something. Whereas here, it's going to look like, just do it like this. Okay, and this will be some value that we assigned once we've created the node. All right. Linked list. So a linked list is just a chain of linked list nodes. So linked list is a chain of linked, or actually I wouldn't say linked list nodes, I'll just say nodes. So okay, there is no real ordering to it. So this could be like 3, this could be 99, and this could be 1. Something like that. So you'll have pretty much a flat one-dimensional structure that enforces no ordering. It's very arbitrary. One node just leads to another of some value. No real ordering to it. Whereas a binary search tree, although it may not look like it, does indeed, and I'll say this is null, null, terminates at null, terminates at null, does indeed have ordering. So a binary search tree a binary search tree is a tree with nodes. Left right nodes. So I just missed the left right nodes. With left right nodes. Left right nodes. Oh, it's like a connected structure. There is an ordering to it. It's subtle. You can't really see the ordering, but there is an ordering. Notice how I decided to put 3 up here, 1 to the left, because again, left is always less than root. This is the root, this is left. Right is always greater than or equal to root. So there is a structure. You have to enforce the structure. So the insertion order for linked list was 3, 99, 1. Same thing for this. 3, 99, 1. So before I get to that, let me kind of describe why this is ordered. Bringing this back, say I decided to insert 3, 99, and 1. Meaning 3, 99, 1. And going forward for the null nodes, I'll just do this. Okay. Well, there are different ways to traverse a tree, and meaning traversal. Let me just say this. Traversal, what does that mean? Traversal means to move around a data structure. So we mean when we say traverse a tree, we're basically saying we want to move through. Actually, instead of through, instead of around, say through. Move through. That's through with two. Move through a tree. 3 ways to do that. 3 different algorithms. Easy algorithms. Basically, first way is called in order traversal. Second one's called pre-order traversal. Third is called post-order traversal. Okay? If we were to do an in-order traversal, what we're doing is we're moving to the left node, right root node, and then the right node. Okay? We're doing pre-order. We're going to basically move, I think, root, left, right. We'll do post order. We're going to do left, right, root. Okay? Let me just make sure we got that right. Pre-order traversal. So pre-order traversal means follows the root left right policy. So root left right. Okay? You can ignore this for now. Then this is left right root. Okay. So I am going to say this is red. This is green. And this is blue. RGB. When we go in order, what we're going to do is, if we have started at our root, we actually, let's say we wanted to print out our nodes, and we wanted to do it in order. Well, when we always start out with our root. Start here. Okay? We'll start our root, but we don't print this out yet. Actually, what we want to do is go to the left child of the root. So step 1. Okay? And then print that out. Once that's printed out, we go back to our root and then print that out because that's the order. Left, root, right. And I'll show you how to do that in code later. Once you're done printing the root, the next is printing to the right. So this will be step 2, and this will be step 3. Okay? And we'll print the right one, which is 99. Okay? Notice how in order almost always leads to a sorted order. 1, 3, 9, from least to greatest. May not be obvious now, but we'll practice on a bigger tree later. Post order or pre-order. Getting a lot of messages because this is work stuff, so bear with me. Again, we have a root left right. We always start at the root. Okay? And we're gonna go we're gonna print the root. Then we're going to go left. So step 1, S1. And we're going to print the left. And when that's done, we go back up. Step 2. We've already printed out the root, so we don't need to go there. But where we want to go is the right. So step 3, which is now 99. Okay. Hopefully you see this pattern in this very small example. Okay, post order means that we want to traverse the left node first, then the right node, then the root node. Again, always start at the root or given root. Come on, pen. There we go. Start. Okay, where do we go? We go left. So we don't print anything out yet. Now we're at the root. We just go left. S1. Print out 1. Then we go back up. Okay. S2. We don't touch this yet. We just directly go down. Actually, I shouldn't say this is S2. We just go back up. But we go back up and then go to the right. And that'll be I'll just say S3. We'll print that out because that's left, right. Go back up. And finally, we print out the root, where it's from. So that's post order. We process the children first. Then we process the root. Pre-order is we process the root first, then we process the children. In order means we're going to process the left child first because that is less than root, so process whatever that is less than the current root, and then process the root, and then process whatever is more than the root, which is the right side. Now having this is not quite clear, so let's go bigger. Let's have a bigger tree. Let's do maybe 20. Then let's do 10. Then let's do 5. Let's do 15. Let's do just do 30. And then let's do, and we have to do it like this. It is, I'm literally inserting. So 25, 35. Okay, this is a nice perfect tree. Okay, so say we want to go in order for this tree. So again, in order was left, root, right. Left, root, right. Where would we begin? Again, start at the root. And then let's actually go to the left. Okay. As it turns out, if you think about it, this is actually a root of some other tree. So the rule is, if we're at some root of some other tree, let's go left. Now we're at 5. Again, as it turns out, we are actually, thinking about it, a root of another tree. It just so happens that this tree here has no left and right child. So we still go left anyway, and we're like, okay, well, we got nothing to print, so we can't go down even further, so let's just go back up. Well, by the rule of in-order traversal here, we've processed the left child relative to this tree here, okay? And so now we had to print out what? The root instead, because we had nothing to print on the left. So we'll print out the root. Now, once we're done printing out the root, let's go to the right. The right of this root is nothing. It doesn't matter. We still go down. Trust the process. There's nothing to print here as a right child. So let's go back up. Okay, we are now done with this tree here. This subtree here. We think of it as its own tree. Now, since this was the left of this subtree, right, we just basically go back up. Since we processed everything to the left here, we printed out 5, which is right here in relation to 10. We'll print out 10. Okay, and then we go to the right. Okay, now, thinking about it again, this 15 here is a subtree of, these two nodes, or this whole tree. And it has these two nodes here as children. So we had to kind of localize this visually to be this, it's its own subtree. So 15, if you think about it, is a root of this tree here. Now, what do we do if we want to go in order? Well, we had to go to the left of this tree. So 15 being the root, let's go left. Oh, we have nothing to print. Okay, so let's just go back up right away. Now we're at the root in relation to this tree. So we'll print that root value out because that's what we want to do when we do traversal for in order. Okay, well, now that we've processed the root, let's actually go to the right of this. Okay, we go to the right. There is nothing. So go back up right away. We'll return. And now we're back at 15. But we're done with that, so it's fine. So now we've processed this entire subtree here. Now, we visualize this again. We've just basically processed this entire... What happened? Oh, I changed opacity. We've just processed this entire subtree, basically. So that turns out to be left of this original root that we came from. So we'll process this root here, which is 20, and we're good. But now we had to process the right side of this tree in relation to 20. So let's go to 30. Okay, before we do anything, now that we're at 30, we had to go to the left because that's what the rule in order says. Left tree first before we process 30. So we go to 25. Okay, well, before we do anything with 25, it's still also technically a tree. So we had to go left. Turns out there's nothing. So we go right back up. Because we processed left already, we'll need to process the root, which is going to be 25 here. Now that we've processed the root, we can go to the right. Going down to the right, well, we have nothing, so we go right up right away. And, well, we've already done 25, so we've technically done all this here. Now let's go back up to 30. And we haven't printed out 30 yet because we had to go all the way to the left first. So now let's actually process 30. And then we'll go to the right. Again, this is its own tree too. It's just that it so happens that the children are null. So now we're at 35. Okay, that's the right side of 30. Well, again, you think about it this way, it's its own subtree. So let's go to the left before we even touch 35 because that's after we hit left. So there's nothing to process, so we go right back up, okay? And we'll process 35 because That's the rule of in order. And then we'll go right. So that's nothing. So we ignore that and we go back up. Then we go back up again. So we're done with this tree here. Then we go back up again. Turns out we've done 20 already, and we're done with this entire tree. So we've in order traversed this entire tree with this number here, or these sequence of numbers here. 5, 10, 15, 20, 25, 30, 35. It's in sorted order. So given some node, we could have even started here. So let's say we started here instead. Well, it would have just been 25, 30, 35. If we had decided to start here instead, it could have just been 5, 10, 15. But we decided to start here, which gave us 5, 10, 15, 20, 25, 30, 35. So this is what we call a recursive. Oh, let me go back to black. So this is what we call a recursive algorithm. Where we're led to just solve smaller subproblems in some data structure. So an in-order algorithm would look something like this. Void in order given some sort of node, which we call cur root. Okay. If we find, there's cases to consider. If we find that we're here, for example, where these things are null, we need to check for it. If cur root is null, then we don't do anything, meaning that we just get out of this function. So we return. Okay, otherwise, we want, given some root, where do we go? We go left, but we do the same thing over and over again. We'll just recursively call in order cur root left. Okay, so then we call that and we process it and say we're done with our left. What's next? Let's process the root, like legitimately print it. So we can do printf and let's just give it a comma. Printf, comma here, cur root value. Once we've done with printing out the root, for example, the root's value, that is, we'll just go to the right side, process everything there. And that's just calling it again. And that's about it. Now, you might be confused. So this is the in order algorithm. You might be confused, like, why printing? Well, this printing here is just some operation that you want to do. It could even be take this current root's value and do something with a database. This part here is where you do something. So essentially, this is just do something. You do something after you call in order, and then on the left child, and before you call in order on the right child. So that's like the current approach to an in order traversal. Now, I want to actually trace this code by hand, just so that you're convinced that this does magically work out. So I'm going to draw the tree again. So in this case, it'll be like 20, 10, I think this is 30, this is 25, and this one was 35, this one was 5, and this one was 15. Okay, Maybe kind of just move it slightly. Oop, too far. Hey, cool. And then I'm gonna write the algorithm again, just so that get some practice. Void in order. We'll call it node. We called it a node, right? Do we call it a node? Cur root. So this represents the current root, like in a frame of reference, in a perspective. And then, of course, if our current root happens to be null, for example, we'll just do nothing in return. Otherwise, in order, what was it? Cur root, again, left side, because that's how in order works. And then we'll print, after we're done with in order, we'll print out the value of the root. Okay, running our room. And in order, the right side. Okay, so let's begin. Well, let's just say, let's do this. Let's just say we start here. Cur root. We'll start here. So we'll say basically in order, and then I'll just do this to represent the node that represents 20. So we call that. Let's see what we get. Well, cur root is 20. Is cur root null? No, it's the node that holds 20. So we don't go to here. Instead, we'll come down here in this code in our execution, and well, let's say this. We want to call in order again. Okay, so let's create this nice thing that represents a call stack. So this is a call stack. And we have basically said cur root is 20. So we called 20. And we're going to call this function with 20's left side. So we say in order 10. Imagine that is basically now calling this function again, going back up with 10 as a value. So we're here previously when we were at 20, but we want to get what is in 10. So we call that function again and pretend that now we're here in this function call. And we're going to say, hey, well, is a cur root, which holds 10, null? No. So we go down here again. And what we're going to do is we're going to get 10's left side and call the function again. So now we're going to dive in again with in order 5 instead, because that's the left side. So cur root equals 5. Great. So pretend we're starting over again in this function call. So is cur root with 5 null? No, it's not. So what we're going to do is we're going to call the function again. So this time with cur root 5's left, right? Cur root is 5. Left is going to be null, but trust the process. Null. Okay? We'll call that function again with this as null. And since we're here, is the cur root, which is null, equals null? Yes, it is. So we return. So then we go back up here. So when we return, what ends up happening is we pop off from the call stack. And now we're back at where we were when we had called this function when in relative to 5. So if we're executing this code, we were here before in relative to 5, this node. So we'll move on to the next line, which is to print f, the cur root's value, which is 5, right? So we'll print here 5. Okay, we're done now with that print. Move on to the next line. Now we're going to call in order cur root right. So cur root is still 5. We're here. We're back here. Remember this arrow here? Well, we're going to call the function again. So at the same level, we're going to do in order. And what's right of 5? Null. Okay? So we're going to put this here. In relative sense, we're making a new function call. And we can look at cur root in this function call here. At the top, it's null. Okay? So we check, is it null? Yes, cur root is null. So we return back to 5 again. So now we're popping that off. Now you're getting lost. The best way to say, okay, what's cur root again? Well, if you forgot to do these arrows, you can always rely on here. Well, cur root is at the top of the stack. So it's 5. And we just finished this here. So next line, nothing. So we've actually finished this whole subtrace here. So we could pop this one off the stack now. Okay. And let's say you visualize it, we're returning back here. Okay. So now what is cur root? Well, cur root is 10, and we just did the entire left side if we kept track. Okay. Well, now let's go to the next line. What's cur root value? Well, cur root is 10. The value of that is 10. Okay? We're not done yet. We have to execute the next line. That's going to be cur root right. What's cur root? We'll look at our call stack. It's 10. So what's right of 10 is going to be 15. So we'll line that up here and we'll say, well, in order, the node 15. And, just put it up here. Okay? Now we're calling in order again with 15 as that cur root node. Check to see if it's null. It's not null. Well, okay, let's go to the left side. There is trust the process, no child, but we still pass in null. And when we do call that, we have to put another call stack entry. And that's going to help us reference null. So when we call this in order function again, because that's what left of 15 is, it's going to turn out to be null. So we return right away back here, pop off the call stack. Okay. And now we execute the next line, which is the printf, and that's 15. Okay. Now we're done with that. Next line, in order, cur root right. What's cur root? Well, we're still at 15 because that's what this call stack shows. At the top of the stack is 15. And that turns out to be null, but we'll just move on anyway and just call it. Okay, cur root is null. Calling in order, since cur root is null, we can just return right away. But let me properly write this down, this call down. Okay, so we'll return right away. Then we can pop off that call stack entry. Now we're back at where cur root 15 is, right here. And we've done the right side already. So run the next line. Nothing else to do. So we're done processing 15. Okay, so what's at the top of the call stack now? Well, we're done with this. We had to go all the way back here. Okay, now where we were at in order 10, we've done everything on the left on 10, right? Because we've done the right side now. We were here. Well, we're done. So pop that off. And now we're back at 20. And basically what you want to do is repeat the process. Now, since we were at 20 and we did process the left side of 20 here, we move on to this printf, which is 20. We'll print 20 out. That's what the cur root is, because that's what the call stack tells us at the top. Once we're done with that, let's go to the right side, because that's what it tells us. So, right side. Okay? So it's going to be in order 25. Oops, sorry, in order 30. It's getting messy. I'm getting tired. So, cur root 30. Awesome. So that's the right side. Now, again, we're at 30. Since it's not null, we're going to go to the left, and that's going to give us 25. Okay? Then we push this in to the next call, 25. And now we're at 25. Well, 25 is not null. So then we go to the left of 25, which is null, returns right away. So let's just write that here just to get the habit. Okay, we're at 25's left. Okay, 25 left is null. We'll call in order. Null, null, return. Okay, so properly do that here. Return back to 25. That's the left side. Pop that off. Okay, pop that off. And then we're back at this printf here. So what do? Well, what's cur root? Cur root happens to be 25. So let's print 25. Then we'll go to the right side. And I'm not going to do this part anymore. I'll just keep doing this. So the right side is going to be null. Okay? Well, since it's null, we'll return right away. We don't print anything now. Okay? So we're done. Okay? Now, no more code to execute in relative sense to, cur node being 25. Okay? So, we're done with processing all of 25 and its children. We pop that out. Boom. Okay, now we're back at 30. Well, since we were in relation to 30, we had called this in order cur root left, where 30 was the cur root. We're done with this because that's where 25 was. We just printf 30. And we'll go to the right side. So that is going to be 35. Okay? Well, 35 is not null, so we don't return. We'll go to the left side of 35 here, calling the function again. That brings us to a new call stack. That's null. Okay, remember these things are null. Okay, now we call that function with null, we return. Okay, there's nothing for us to do there, so we pop that off. And then what ends up happening is, well, now that we're done with this part where cur root is 35, we just need to print 35. Okay, and we'll go to the left side of 35, which is going to be null. So we'll make a new stack entry here with null. Call that function. Cur root is null, so we return. So we don't need that anymore. Come on. Okay, so cur root is 35, and we've already processed the right side, so we're done with that. We returned. Okay, now we're back at where we were at 30. Okay. Ugh. Excuse me. We were back at where we were at 30, and we have no more code to execute because we've already processed 35, so done with that. And then now we're back at 20, and we've already processed 30, which is the right side of that, was done. So we're clean. We are done. So this is actually the output here. 5, 10, 15, 20, 25, 30, 35. So that was like the code of the in-order traversal and its trace. Yeah, it's kind of awkward to do when you haven't done like recursion before. But you have to kind of just find some way to keep track of all these calls that you're just calling and calling and calling and calling. And then when you return, that's when you kind of come back up. And a tree is basically a recursive structure. So next time we're gonna actually go through pre-order and post-order. We're gonna do this slowly so we understand. But this is actually the gist of a binary search tree in order traversal, where this printf represents a do something, and then data structure wise, this is the code that represents a binary search tree node. So we're kind of like writing code as we go along, and then maybe like when we got this traversal down, we can actually kind of test it out in code. So next time. Thanks.